Hi everyone, welcome to the 6th video in the GeomAlgoLib series, and in this video we will continue with our ConvexHull3D algorithm implementation. I know it's stretching a little bit because this is the 4th video in the ConvexHull series, but I promise you that it's going to be worth it in the end. We're going to have a very high performance ConvexHull algorithm written in C++. If you haven't seen the last 3 videos on this algorithm, I strongly recommend that you go check those out. You should be able to find the links to those videos in the description. And without any further delay, let's just jump right back into the code and pick it up where we left off in the last video. Let's just hop back into our header file. The next method we want to write is create initial simplex. So actually the create initial simplex method is slightly long. So let's just do the easy ones first. Let's just do getFace. So first we need to check if a face with that ID exists in our faces map. So I'm going to call this match. And okay, I typed the name of the field wrong. It's mfaces, not singular. If we found a match, then we need to set the match that we found to the output parameter. It's match, the second of match, because match is a pair, key value pair. And then we successfully found a match, so we return true. And if we haven't found a match, we return false. The next method we want to implement is getEdgeFaces. So for the given edge, we want to find the pair of faces that are connected to this edge and return those faces. Set those to this return parameter. So let's try to find a face pair for the given edge in our map. We may or may not find it, so let's call it match. If we find a valid match, then let's set the faces that we found to the output parameter. And because we found a successful match, we return true. If not, we return false. And now let's add the logic for the face center method. This one's really simple. So you just return the average of the 3 vertices. And that's that. Let's also do the copy faces method, because that's also another easy one. So in this method, we're going to just loop through all the faces and copy the indices of the vertices for those faces into this flat array, which in the end is going to have a number of elements equal to 3 times as many faces we have, because it's a flat array. Okay, so the next function that we're going to define is create initial simplex. So let's jump into the definition in our source file. So here's what we need to do in this function. We need to select 4 points from our collection of however many points, and we need to create a simplex, a tetrahedron out of these 4 points. So creating a tetrahedron out of 4 points is not a challenging task. That's the simpler part. But the more difficult part is to select the best combination of 4 points possible. So the way we do it is to try and maximize every dimension along the way as we select 1 point at a time. So the first thing that we need to do is to find all the extremities, the points with highest and lowest x coordinate, highest and lowest y coordinate, and highest and lowest z coordinate. So let's start by creating an array which can take 4 indices, and these will be in the end the indices of the 4 points that we select for creating our tetrahedron. But we can't hope to ever create a tetrahedron if the total points in the convex hull is less than 4, right? So let's add a check for that. If the number of points is less than 4, we simply throw an exception. And if the number of points is exactly equals to 4, then we just populate the best, populate this array, the best indices array, with the indices of the 4 points. So we just do that. But if the convex hull has more than 4 points, then we have the task of picking the best combination of 4 points. So we're going to create an array that stores the extreme coordinate values, and it's going to have 6 elements in it. So the first coordinate will be the lowest x value, then the highest x value, then the lowest y, then the highest y, then the lowest z, and the highest z. So the next thing that I'm going to do is to loop over all the points that we have and find the highest x coordinate, lowest x coordinate, highest and lowest y coordinates, and z coordinates. This part is not really that complicated, so I'm just going to do it without talking through the whole thing. So once we exit this loop, our bounds array and our extremes array, they're both populated with the right data. Now our task is to go through all the points in the bounds array and find the best combination of 2 points that are the farthest apart from each other compared to any other combination among these 6 points. So we're trying to pick a combination of 2 from 6. So that gives us a total of 30 choices, 6 times 5, right? So it's not a lot of choices. We can just search through these choices exhaustively. And the whole creation of initial simplex is only done once, so this doesn't cost us so much in terms of performance. So let's just do an exhaustive search through a nested loop and go through all the bounds. So let's create some helper variables outside. And let's put the point corresponding to the outer loop in our helper variable. Then we start our nested loop with the loop variable as j, your classic ij combination. Then we measure the distance between the 2 points as the point that we stored minus the second point. That gives us a vector, and we want to get the length of the vector, but this is only for the sake of comparison because we're just trying to maximize the length. We might as well use the squared length, right? So in fact, let's create these variables. So if the measured distance is greater than the maximum distance that we know at this point in time, then we say we recognize the combination of I and j as the first 2 of our best 4 points. So let's assign best 0 as bounds I and best 1 as bounds j. And let's update the maximum distance as the new maximum distance that is calculated. So by the time we exit this loop, we have found the first 2 of our 4 best points for our tetrahedron. So a small correction. Earlier I said that there's 30 different ways to select 2 points from a set of 6. I was wrong. I got confused because there's 30 permutations, but the actual number of combinations is only 15. Another correction is that in our second loop, the inner loop, the one with the loop variable j, we don't actually need to start all the way from 0 again, because we're only interested in checking for 15 combinations of 2 points at a time from a set of 6 points. We can just start the inner loop from I+1 instead of 0 to be more efficient. So I made this change later because I didn't realize that I made a mistake when I was recording this video, writing the code. So if you go to the GitHub, you should be able to find the latest code without this mistake. But for now, let's continue with this redundant code. So when we get here, the maximum distance should be it should represent the farthest possible distance between any 2 points and the whole collection of points that we have. But for some reason, if the collection of points is somehow degenerate, if the points are all coincident, or if there's not enough points, or for some reason there's something wrong with it, we could get some odd values. So just to screen out those odd values early in the process, let's check if the max distance is less than or equal to 0, and if it is, then we just throw the same exception. Okay, so we've chosen 2 out of 4 points that we needed to choose, right? Next, we want to choose a third point. So the first 2 points that we chose give us a single line segment, right? We're still a long way from building an entire tetrahedron. So now our job is to choose a third point, and we're going to choose a point that is the farthest away from the line that we created using the first 2 points, right? So to do that, we're going to loop over all the points one more time. And like I said, don't worry about the performance. The whole process of creating the initial simplex has to be only done once, so it's not that much of a performance hit for our algorithm. So let's once again reset the max d value so that, for a new loop. So to measure the distance from the line segment joining the best 0 and best 1 point, let's create a reference point, which is the point that we selected as our first best point. So that will be point with the index best 0. And let's create a unit vector in the direction of this line segment. Let's call it unit direction, in short UDIR. And it's going to be the point with index best 1 minus our reference point. That gives us the vector that represents the line itself, but we want the unit vector of that. So we're going to use that unit vector to measure the distance from the line to the new test point. And now we're going to loop over all of the points one more time. And we're going to measure the distance of the point, of the test point, from the line as follows. So we want to get the vector from the reference point to the test point. So that is that represents the vector from the reference point to the test point. And now we want to get the component of this vector that is parallel to the line, the line that joins best 0 and best 1. So that component, I'm going to put it in parentheses here, is u direction vector times the component of that vector along the u direction vector, which is once again the dot product, because u direction vector is already a unit vector. And this is the parallel component, and we have to subtract this parallel component from the original vector to get the perpendicular component, and the perpendicular component represents the distance. And once again, for comparison's sakes, let's use the squared length of this perpendicular vector. And if this distance is greater than the maximum distance that we know so far, At least in the first try, it has to be greater than that because we start with a double minimum value. Then we identify this as our next best point and update our maximum distance with the new maximum. And by the time we exit this loop, we will have found our third best point. And just to make sure that nothing went wrong, let's perform the same check again, just to make sure that there's no strange degeneracies in our point collection. And now we have to choose the fourth point and the final point. And this time, we have already chosen 3 points, which means we have defined a plane. We know it's not a degenerate plane because both times the max d was greater than 0, which means it's a triangle with a non-zero side length and a non-zero height. So it's not degenerate. And now for the fourth point, we are going to try and choose the point which is the farthest away from the plane of this triangle. And for that, we're going to one more time loop over all the points. But let's again reuse the same max d variables by resetting them to the double minimum value. And let's define the u direction this time as the normal of the triangle that we created with our first 3 best points. So it's going to be... Okay, so the first best point, the best 0 point, is already stored in the reference vector ref. So we're just going to make use of that. So if we subtract that from our second best point, that gives us one of the edges of the triangle. And then if we take a cross product of that with what we get by subtracting the next best point, subtracting the reference vector from the next best point, that gives us the cross product vector, but since we're only interested in the direction of the normal, we have to take a unit vector. Now, let's start looping over all the points. And for each point, we can measure the distance to the plane as the absolute value of the dot product between the unit vector, which represents the normal of the plane, and any vector that connects any point on the plane to the test point. So our test point is this, MPTSPI. If we subtract the reference point from that, we get a vector connecting a point on the plane to the test point, and when we do the dot product with the normal, then that gives us the length, the perpendicular distance of the point from the plane. And if this distance is greater than the current known maximum distance, then we will choose that as our fourth and last best point and update the maximum distance as the new maximum distance. So by the time we exit this loop, we have found our fourth point. And one more time, we are going to repeat the same check again, just to make sure that there's no degeneracies, that the fourth point was not coplanar with the triangle, and if that is the case, we will throw an exception. So now, when we are here in line 314, we have chosen the 4 points that we want to build our simplex with. So the next task is to simply create the 4 faces for the simplex. And we're going to put them in an array named simplex. The array length is of course 4. And we will just assign the faces manually. So yeah, to get the faces of a tetrahedron from 4 points, you have to just connect all combinations of 3 faces, and that's how you get the faces. So I'm just going to type it out without any explanation. It's very simple, especially given that we don't have to worry about the orientation and the normals of these faces. So just another side note is that the one input parameter that this function receives is the face index. So this is sort of the current running index of triangle creation in our attempt to maintain a unique ID for all the triangles being created. So let's just use this running index and increment it whenever we create a triangle. And the first triangle . Okay, so that is all 4 of our triangles. Now that we have a tetrahedron, and now that we have the 4 best points, the 4 vertices of our tetrahedron, we can define the M-center field of this structure, of this class, which is inside the tetrahedron. So it has to be the average of the vertices of the tetrahedron. And as you know, we are going to use this as the point that we know to be always inside the convex hull. So we're going to define this as, you know what, let's just write a loop instead of actually typing the whole thing out. Let's initialize it as 0, and then let's loop over all the best points. Then let's divide it by 4 to get the average. And now the only thing left to do, well, that's not the only thing, but one of the last things that we have to do still is to take all the faces that we just created, all the 4 faces that we just created, and add them to the hull. So let's once again loop over all the faces. And before adding the faces, let's just make sure that none of the faces that we just created are invalid, just as a final, check. If it's not valid, let's just continue. We don't need to add it. But if it is valid, then we will just set face. And if you remember, the set face function accepts the parameter, we have to pass it by reference. So this set face method takes care of flipping this face if necessary. So the order of the vertices will be changed, and the normal will be flipped if necessary, and the center will be used to make this decision of whether or not to flip the face. So that's taken care of. Because we finished creating our initial simplex, we have our seed convex hull that will serve essentially as a seed to the rest of the algorithm. So when we created this convex hull, some of the points that we started with will end up on the inside of the tetrahedron. And for all future calculations, we don't want to think about these points, so we have to filter for these points and remove them from our outside points set. So let's do that by looping over all the points and checking if they're inside the tetrahedron. So to do that, I'm going to create a vector that can store the indices of the points to be removed. And then I'm going to loop over all the points that are outside. So I'm going to call them outside point indices. OPI stands for outside point index. And for each point that is outside, let's have a helper boolean that we're going to use inside the loop. And we're going to set this outside boolean to false. So we're going to assume that every point is on the inside unless proven otherwise. So let's try to do the proving otherwise part by looping over all the faces of the simplex. And let's say if this particular face of the simplex contains this vertex. So the point that we are checking for is one of the vertices of the tetrahedron. Then we definitely know that this point needs to be removed from the future calculations. And furthermore, we don't need to continue checking, comparing this point with the next face of the simplex. So let's just break out of this inner loop of simplex faces. But let's say if the point that we're checking for is not one of the vertices of the face, then we have to check if the face is visible from this test point. So let's use our face visible method and pass the simplex face and our test point. It's simplex, not simple. So if we're inside this if block, that means the face is visible, and that means this point is outside that face. So you only have to be outside just one face, and we don't need to check any further. We can just break out of the loop. And once we are outside the loop, if the point is not outside, which means it's not outside any of the faces, which means it's inside all the faces, which means it's inside the tetrahedron, then we can just add this point to our vector of indices for removing for the points that need to be removed. So by the time we exit this outer loop that's looping over all the outside points, we populated all the points that are inside the tetrahedron into this remove points vector. Well, we populated this vector with the indices of the points that need to be removed, and all that's left to do is loop over these indices and remove them. So that's it. That finishes everything that needs to be done in this method, in the create initial simplex method. And in theory, if we build it and run it now, we should get our convex hull. I mean, not quite, because we haven't yet connected any of this logic to C# yet. We have to create our pinvoke method and then also implement a method to convert this raw data into a Rhino mesh to be visualized, because without that we can't visualize or make any sense of the data that we're getting from the ConvexHull algorithm. But what we can do now is to just check if it builds without errors or if there's any problems. Okay, our C++ project builds without errors. So that wraps up this video, and in the next video we will create our pinvoke function in C++ and use it from within C# and try to see some results. Thank you for watching, and see you in the next one.